Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed about linear discrete model, where we have considered also the examples. So, linear discrete model means we have just considered either it is of first order or second order differential equations. In the first order case, we have considered the examples of a cell division model, and in the second order case, we have just considered the Fibonacci Revit model there. So, in this lecture we will just consider that linear discrete model for a system of equations, and in this lecture we will just go for the linear prey-predator model, then we will just go for the stability analysis of linear systems based on matrix approach, and in the last content of this lecture we will just go for the graphical solution of first order linear differential equations. So, if you just consider this linear prey-predator model, we have to consider like a prey and a predator for this model here. So, if you just consider a forest containing only tigers, suppose, that means predator, and a deer, suppose it is like prey there. The tiger kills the prey for food, and suppose at a time instant n, if we will just consider Tn is the like a tiger population at the end of year n, and Dn is the population of a deer at the end of year n there. So, in order to formulate this prey-predator model here, so we have to consider certain assumptions. So, the assumptions are like that. First, we have to consider deer are the only prey for tigers and tigers are the only predators for deer. So, no dependencies of other factors will be considered for this prey-predator model. Second assumption, we have to consider that tigers will die out in absence of deer, but deer population will grow in absence of tigers also. So, this means that when this tiger population will grows off, then the deer population will decline, and when this deer population will take the increments, then again the tiger will grows off. But certain population levels should be there, that in order to existence this like a tiger population or the deer population. So, third assumption, if you will just consider like in presence of deer population, the rate of tiger population growth increases, and in presence of tiger population, the growth rate of deer population declines. That whatever I have just told here. So, if you will just go for like the construction of this linear prey-predator model here. So, further we have to assume that suppose first A, that is the rate at which tiger dies in absence of deer suppose, and B is the rate at which tiger grows in presence of deer. So, this means that whenever the tiger is present and deer is present, automatically when these tigers will eat the deers, then the deer population will decrease and the tiger will give birth to other tigers, then this tiger population will grows it up. And if you just consider like C, suppose is the rate at which deer grows in absence of tigers. So, certainly after some time, if you just find that enough tigers are present, then these tigers will not find the sufficient food and they will just start dying. And when it will be balanced with again with the deer population there, then again this tiger population will grows it off. So, in that case, suppose we are just assuming that D suppose is the rate at which deer dies in presence of tigers. Hence, at that time level, suppose at time level we are just considering as n here, if you just take the difference of like the tiger population at n plus 1 time steps and nth time steps, then we can just signifying here that term as del Tn here, which is represented as Tn plus 1 minus Tn. And since we are just writing here the rate at which tiger dies in absence of deer as the rate is A here. So, that is why this tiger will be declined at a rate A, that is why we have just multiplied it as minus A into Tn here. And in the absence of this tigers, if you will just find this deer population will grows it off. So, that is why we have just write it as, that is B is the rate at which a tiger grows in presence of deer here. So, that is nothing but B Dn here. And if you just see this difference of like deer populations at two different time levels, that is at n plus 1 and n here, which is represented as del Tn as dn plus 1 minus dn. So, then that can be represented as this deer population will grow Gt of when this tiger population will decline. So, that is why if we will just consider here rate at which deer dies in presence of tigers, that is as minus d here. So, then this rate of decline of tiger will get increase the deer population there. So, if we will just formulate this model in a matrix formulation here, since we have like the quantities as t n plus 1 here, then d n plus 1. So, these are this like next time step calculated values for tigers and deers here, and we want to kept these terms in the like left hand side here. Then this can be represented as like 1, since a Tn it is present in the left hand side, if you will just take to the right hand side, we will have this quantity as 1 minus a here, and b itself it is present there. And if you will just consider here dn to be come to the right hand side here, then that will be take the value as 1 plus c here, and which is written as 1 plus c, and then minus d Tn it is there. So, that is why this quantity is taken as minus d here. And as usual, this matrix multiplication values we can just keep it as Tn and Dn there itself. So, if you just go for like a stability of this linear system here using this matrix approaches. So, we have to consider like a system of equations there. So, that is why it can be represented as a vector elements as a matrix. That is, if you just represent this system as in the form of Wn plus 1, this takes like two population levels there, that is Tn plus 1 and Dn plus 1, which can be represented as the complete matrix A, which took this like the coefficient elements of Tn and Dn as 1 minus A, B and minus D, 1 plus C here. Then it can be multiplied with this Tn and Dn, that is why we can just write Wn is the factor which takes the values Tn and Dn there, where A is called your coefficient matrix, and any point in a system especially it is called an equilibrium point or a critical point, or sometimes it is said to be steady state, if we will just consider this Wn plus 1 is 0. And for that, if we will just go for this stability of this system, we have to find the eigenvalues of this matrix there. So, to find these eigenvalues of any matrix, we will just go for these characteristic equations. So, if we will just represent this matrix A in a characteristic equation form, then we can just write the system 3.2 as a determinant of A minus lambda I equals to 0. Suppose this eigenvalues are represented as a lambda I here, or the eigenvalues of the matrix A, and if one of this lambda I value is greater than 1, then the system is unstable. Already in the last lecture that we have discussed. This means that the system will goes out from the origin. So, that is why we are just writing this as unstable about the equilibrium point. And if all lambda I is strictly less than 1, then the system is said to be stable. This means that automatically it is just tending towards the origin whenever we will just go for higher powers of lambda I. So, that is why the point is said to be stable at equilibrium point. And if all lambda I is less or equal to 1, this means exactly one value, if it is achieving the value as 1, then the system is called asymptotically stable about equilibrium point. This means at 1 it will just fix a line there. So, that is why spirally it will just come towards like the critical point. If it is existing there, then the solution will just approaches towards the point in that situation. So, this is the third point we have just considered, either it is less than 1 or at least one of this value should be equals to 1 there. So, if you just go for an example of any linear prey-predator model. So, suppose for example, if we are just considering a prey-predator model for two species, that is represented as x and y. Suppose if we in the last slides we have just considered as tigers and deers. So, if you just consider x as the tiger population and y as the like deer population. So, then we can just write x is the predator and y is the prey. So, the prey's growth rate is suppose 1.2, while that of predator is suppose 1.3 here, and prey's population reduces by factor of 0.3 times that of predator, while predator's population increases by 0.4 suppose that of prey's population. So, we have to construct a discrete time model and we have to justify the stability based on these approximations. So, from the given data, if you just formulate this model, then like we have just defined in the previous slide as like A is the rate at which tiger dies in absence of deer, or B as the rate at which tiger grows in presence of deer, C is the rate at which deer grows in absence of tigers, and D is the rate at which deer dies in presence of tigers. Then if you will just consider all the coefficients in this problem here, or we will just relate that problem to this problem here, then we can just find A is the quantity, that is the predator population increases by 0.4 times that of prey's, that is nothing but the quantity A there. And if you will just consider here, that is the prey's growth rate is 1.2 while that of predator is 1.3. This means that B is 1.3 and C is 1.2. And finally, prey's population reduces by factors of 0.3 times that of predator, that is nothing but D equals to 0.3 here. Hence, the formulated model, if you will just write like xn plus 1, this equals to 0.6 xn plus 1.3 yn. Since we are just writing that is as a negative of 1 minus 0.4, so that is why it is just coming as 0.6 here, and specifically B is present independently, so that is why it is written as 1.3 here. If you will just see here, that is 1 minus A, B and minus D, 1 plus C. The same quantities we are just writing here, that is a 2.2, since we are just writing that one as a 1 plus C there. So, that is why 2.2 into yn it is present there, and minus 0.3 xn it is present there over. So, if you just write this coefficient matrix here, then this coefficient matrix can take the values as 0.6 for the first coefficient here, then 1.3 as the y1 coefficient, then if you just see xn coefficient here, that is nothing but minus 0.3 here, and yn coefficient that is written as 2.2. If you just write this one in a matrix multiplication form, then we can just write A x s here xn yn. So, this is the complete system we can just represent, and to get this eigenvalues of this coefficient matrix, suppose, then we have to solve this system, that is A minus lambda I equals to 0. So, you can just put here 0 minus 6 minus lambda here, 2.2 minus lambda here, and find the determinant. Especially we can just write this is as nothing but A minus lambda I, this equals to 0 here. Then we can just write this one as 0.6 minus lambda, 1.3 minus 0.3 and 2.2 minus lambda, this equals to 0. So, if you just do this multiplication, like we will just do here 0.6 minus lambda into 2.2 minus lambda minus of minus, this will just give you plus here 0.3 into 1.3, this equals to 0 here, and we will have a quadratic equation. And if you just find the roots are like lambda 1 equals to 1.4 and lambda 2 equals to 1.9 here. And the generalized solution, as we have discussed in the last lecture, that can be written as a like complementary function, which has been of the form xn equals to c1 into lambda 1 to the power n, c2 into lambda 2 to the power n, that is nothing but 1.9 whole to the power n here. Similarly, the other solution that is in the form of yn here, that can be written as a c3, your first solution, that is lambda 1 to the power n, c4 into lambda 2 to the power n here. So, now if you just substitute these equations back in the system, one can get rid of 2 constants out of 4 constants here. If you just see these 2 variables xn and yn, this involves 4 constants here, c1, c2, then c3 and c4 here. So, if you will just go for the solution in a like a successive iteration method form here, then we can just write this equation, that is as xn plus 1 equals to 0.6 xn plus 1.3 yn here. So, we can just write this modified form of this yn term as xn plus 1 minus 0.6 xn as 1.3 yn here, and in xn, if you will just replace this as xn plus 1 here, which can be written as C1 1.4 whole power n plus 1 plus C2 1.9 whole to the power n plus 1. So, that we are just replacing here in terms of xn plus 1 minus 0.6 into the solution, whatever it is just written C1 1.4 whole to the power n minus C2 1 to the 1.9 whole to the power n here. So, this equals to 1.3 yn here. So, which can be written as like this C1 into 1.4 whole to the power n plus C2 1.9 whole to the power n, and one coefficient it can be taken as 1.4 outside and 1.9 it can be taken outside, and that can be written in a modified form. And in that sense, if you just find the values, that is nothing but 0.8 C1 into 1.4 whole to the power n plus 1.3 C2 1 to the power 1.9 whole to the power n, this equals to 1.3 yn here. And if you just divide 1.3 on the left hand side, then we will have like 8 by 13 C1 into 1.4 whole to the power n plus C2 1.9 whole to the power n, this equals to yn here. And the absolute values of both the eigenvalues are greater than 1, and hence the system is unstable about its equilibrium point 0 0. And if we will just go for the like conditional checking of what do you mean by unstable system here, this means that the process will go on and will never settle. This means that even if the tiger will be present and the deer will be present, so then both these population will grows it off. Even if the tiger will be catch or like kill the deers, and deers will also be like it is killed by the tigers, but both the populations it will just grows it off. So, this is the thing that when predators will increase, prey population will go on increasing, and vice versa. Similarly, if the tiger will dies out, then this like deers will also dies out. So, we cannot control the situation. Now, if you will just go for the analysis of these situations in a better way, when one of this lambda I is less than 1 and when both these lambda i's are less than 1. This means that when one of the lambda I is less than 1, then other lambda we do not know how it will just perform there. Maybe we can just control one variable, but other variable how it will just perform we do not know. And when both these lambda i's are less than 1, then we can just say that the system is going towards like a stable condition there, and we will have a like certainly definite solution there. So, if you will just go for this graphical solution of a first order difference equations, so far we have discussed only the analytical solution of linear difference equations with constant coefficients. But if we have given any general difference equation of first order to solve, will these methods help us? So, definitely it is no. So, in that situations these methods will not help you out to get it out. So, that is why we need a graphical solution method where we can just check the stability whether the solution is moving towards the equilibrium point or not. So, with analytical methods it is not always possible to obtain the solution due to certain limitations. Hence, we need some other general method to deal with any kind of difference equations. And in this case, graphical method may help us in analyzing the situation, although it will not gives us the equation form of model, but it will help us to understand the behavior of the system, whether it is just going towards the equilibrium point or towards the origin, or it is just deviating from the origin and going towards the outside. And the way of solving these differential equations in a graphical sense is called co-observing method, and this method is only applicable for first order equations only. And in the previous slide we have also explained here, if you just compare these coefficient values in C1 and C2, and we can just relate these variables with these yn coefficients, then at that time we can also establish this relationship between C3 and C4 also, that you can just derive in your form. So, first if you just go for this graphical solution of difference equations, let us consider the first order difference equation, which is written as xn plus 1 this equals to f of xn, suppose here. The methodology to draw co-waves is as following suppose. That is, first draw the graph for y equals to f of x and draw a line y equals to x, mark all the intersection points with the curve of y equals to f of x, and take an arbitrary point a1 suppose as the point x0 0 on positive x axis and put a vertical line up to the graph of y equals to f of x. Here you will get the point a2 as the point of x0 f of x0, that I will just show in the next slide. From point A2 move horizontally, if you just see that you will have like a graph here and you have this graph like y equals to x is existing there. Then arbitrarily you are just choosing any point here x0 and you will have a functional value along this line here f of x0, and the coordinate you can just define as x0 and f of x0. Then just draw this line, then you can just draw this line along this way, then you will just put this, then you will just go in this in that form, and finally you can just reach that I will just explain in the next slide here. So from this point A2 move horizontally towards the line y equals to x and stop at A3 equals to f of x0 f of x0. Now say x1 equals to f of x0 is there, again move vertically from point A3 to A4, that is the point of x1 f of x1, and call x1 as f of x1 there. Repeat this process moving alternatively in horizontal and vertical directions till you find the pattern. The resulting polygonal path is termed as the curve wave graph or simply a curve wave. So if you just see this slide here, first we are just considering the basic example that is in the form of like f of x equals to 0.5x suppose, and if you just plot this coordinates here as in the form of like this one here, then directly we are just putting y equals to x line, and if you just put this line y equals to f of x as 0.5x as we have explained in the previous slide, then we are just considering any arbitrary point, suppose x0 is any arbitrary point on the axis here, then we are just pointing this point on this graph of y equals to f of x here, and next if you are just plotting or putting this like perpendicular line or the functional values along this like y equals to x line, then this line will be represented in this form here. So then we will just put this like functional values of the point along this line, that is the functional value here. Then again we will just go towards this rotation of this line towards this point. Since x1 is known to us, then f of x1 we can just find and put this perpendicular line on the y equals to x line there. And finally if you will just plot again this line, then this will just go in this direction, then it will just go in this direction, then it will just go in this direction. So likewise you will just move towards the origin there. Here one can observe that all the vertical and horizontal motions are monotonically decreasing, and hence the system is stable here. So if you just go for like a similar solution for a function like f of x equals to 0.8x here, and this f of x equals to 0.8x, it will just lies above the line y equals to x, and if you just see here any point, if you are just considering like x0 is the point on this axis, then the corresponding functional values along this function y equals to f of x will be like x0 and f of x0. Then we can just plot the perpendicular line along this line y equals to x there, and again if you just take this line, that will just go outerwards towards the origin. Hence we do not have like the stable condition here. This means that we are not moving towards the origin or the critical point, it is just going outwards there. Hence we can just conclude that all the vertical and horizontal motions are monotonically increasing, hence the system is unstable here. So if you just go for the analysis of a linear cell model by curve wave here, since a linear model we have just considered cell division model as Cn plus 1 equals to alpha Cn, and one can easily verify the analytical solution with curve wave graphs for different values of alpha here. if you will just go for these equations which I have analyzed by co-waving so far has equilibrium point at origin only, that is homogeneous linear difference equations. Now, if you will just think for the nature of co-wave graphs for non-homogeneous equations, will they differ by homogeneous one graphically? Yes, definitely it will differ. And what about the stability, whether it will just move towards the stable conditions or not, especially you can just find that it is no change. So, if we can just go for the like matching of the results with the analytical solution, we can just verify that this non-homogeneous equations, it will just differ when they appear in a graphical sense with the homogeneous models. Since already we have seen that non-homogeneous equation differ only at equilibrium point and will not affect the stability. Graphically, it means that the graph of f of x will get shifted by the parameters situated at the right hand side. Here it is like a m, if you will just see, that is all the points. If you will just verify, then you can just find that this is just satisfied by the value of m. And then we will just go for the summary of this lecture, that is linear pre-operator models, that is formulation and solutions we have discussed here. Then we have discussed about solution of linear systems and their stability analysis. Then we have just discussed about their graphical method and first order differential equations. Thank you for listening this lecture.